Alright, so I just introduced the first type of improper integrals. These are limits at infinity. So basically there are two or three types of integrals. You're integrating from, I'll use yellow to mark what I'm talking about. So like the first type here is if you're doing an integral from some number up to infinity. The second type here is if you're integrating from like negative infinity up to some number. And then the third type here is integrating from negative infinity to positive infinity. So geometrically, the idea is now you're calculating the area of some shapes that have infinite base. So like the area can go from like 0 out forever, or it can go out to the right. That's like case 1 here. So you're, again, imagining a situation where your graph, like if this is A, you're considering you have this sort of horizontal asymptote, and you're calculating that area on forever. In case 2 over here, you maybe have something like you're coming out from the left, and you have some graph or something, and you stop at some point A, and you're calculating the area. This is just a schematic. The area goes on forever. The base will continue on forever to the left. And in situation 3 here, it's like if you have something that just, it's going to be kind of close to 0, but it goes out in both directions forever, so it's going to be kind of thin, and you want to know what that area is, which again is intuitively very strange, because all of these bases are of infinite length. So like this distance here would be infinity, because it keeps going on forever to the left. This distance here is like infinity, because it goes forever, and similarly in case 3. But anyways, and then here are the formal definitions. Just by taking limits, so it's not a big deal. And now, just so you get a feel for it, let's just do a couple of examples to practice with these calculations. So it's really not too bad. Okay, so here's the first example. Let's calculate the integral from 1 to infinity of like 1 over x squared dx. So, well, we just use, again, we're in situation 1 over here. So by definition, this is just the limit as b goes to infinity. You don't have to use the symbol b, you could use any symbol you want, but 1 to something as that something gets bigger and bigger and bigger and bigger. Okay, so now we just need to, doing this decomposes into sort of 2 steps. We have to first do the integral, and then we have to take the limit as b goes to infinity. Anyway, so let's just keep going. So we're taking the limit as b goes to infinity of the integral from 1 to b. And in order to do this integral here, it is much easier to just use the power rule. So let's just write it using exponential notation like that, and then we can use the power rule with the fundamental theorem of calculus. So we're still taking the limit, and then now we're going to use the fundamental theorem of calculus. So that says we take an antiderivative. So you increase it by 1, negative 2 plus 1 is negative 1, divided by that. We have to evaluate this at the 2 different endpoints. The endpoint here is, the endpoint here is 1, and the endpoint here is b. And again, that's just a shorthand notation for the following. Still, we can ignore the limit for the moment. So that means you're going to plug in b in here. So you get b to the minus 1 divided by minus 1. And you subtract from that, you plug in 1. So that's 1 to the minus 1 divided by minus 1. Okay? So all I'm doing here is I'm just expanding the meaning of this. Okay? So this is, the fundamental theorem of calculus. Fundamental theorem of calculus. It says that to evaluate a definite integral, you find an antiderivative, and then you plug in the top value first. This top value comes over here, and you subtract from it, plugging in the bottom value. Anyways, so now we're just going to continue with this calculation. Still, before we take the limit, let's just work it through. So, what does this look like? Well, b to the negative 1, so that's like 1 over negative b, and then we have minus, well, this is just 1 over negative 1. And now as b goes to infinity, now we can formally take the limit, and remember limits actually are very well behaved. So as b goes to infinity, so you're dividing by something that's getting larger and larger and larger, and larger and larger and larger. I mean, it's negative because of that negative b, but you're like dividing by negative 10, dividing by negative 1,000, divided by negative 1,000,000, divided by negative 1,000,000,000, and if you divide by a huge number, you get a tiny and tiny and tiny and tiny number. So when you take the limit, this thing actually just cancels out, just goes away when you actually calculate the limit. So when you calculate the limit, this term just goes away as b goes to infinity. And so you're just left with this thing here, and this thing here is just negative of 1 over minus 1, which is positive 1. And so that's the answer. So I'll just, so you can look up here for a second. So this integral is just equal to positive 1. So I'll just summarize the work. So we calculated that the integral from 1 to infinity of 1 over x squared dx is 1. And that's it. So again, you can think about this geometrically. It's very kind of bizarre. So the picture, if you want to have a picture for what's going on, the picture is, you look at the graph. We know that 1 over x sort of has this asymptote, 1 over x squared is similar, so graph it like looks like that, and it keeps, so I'm graphing here y equals 1 over x squared. Here's the y-axis, here's the x-axis, and say here's 1, and so what we're doing, this thing goes on forever. It is always positive, but it gets smaller and smaller and smaller, right? Like 1 over 100 squared, 1 over 1,000 squared. It keeps getting smaller and smaller and smaller. And so it's kind of wild if you think about it, but we are actually calculating the area, and this thing literally goes on forever, but it keeps getting more narrow the further to the left you go, or sorry, to the right you go. It's narrow, 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 and this thing actually has, even though it's a shape with an infinite base, it actually has this finite area, and the area of this region is actually equal to 1. That's what this calculation has showed us. So that's the first example. But anyway, the example is just how the calculation works. So it's really no different than calculating integrals. Now you just have to throw in this process of taking limits. That's sort of the only thing that's new. Alright, so let's do a few more examples. Here's another example. And this example shows that you don't always get a number, so the answer may not always be finite. So in example 1 here, we saw that even though the limit of integration is infinity, the actual integral is the number 1, but that's not always the case, so you do have to be careful. So here's another example. If we did 1 over x dx, so let's just set it up right away using exponential notation. So that's x to the minus 1 dx. So formally we take the limit as b goes to infinity of the integral from 1 to b of x to the minus 1 dx, and then we can use the fundamental theorem of calculus inside of the limit. So we're still having the limit, but now we're going to do the fundamental theorem of calculus, which says that we find an antiderivative of that. In this case, the antiderivative is natural log, so you get natural log of b minus natural log of 1. Now, you may or may not know this, but it's okay if you don't. Natural log of 1 is, this is actually 0. So, so this is just the limit as b goes to infinity of natural log of b. And remember, the natural log of b is saying, like, what power of e, this Euler's number, gives you b. But as b gets really, really large, you'll need a larger and larger and larger powers of e, so that this thing is actually infinity. So we write it like that, even though infinity is not a number. And we're done. So we're done. So summarize, I'll just rewrite the statement. So 1 over x dx is actually equal to infinity. So we could also say, like, it does not exist. So there's actually, the integral doesn't actually equal anything. It's just the area under the graph. So now, my picture here isn't very precise. It's going to look very similar because I'm just doing rough sketches. But now you're looking at the graph of 1 over x, and it's sort of like the same. You can't really tell the difference between this picture here versus this picture over here. But it turns out now that this thing is a little bit thicker than this over here, and the area here is actually infinite. So there's kind of a subtlety. You might think that 1 over x squared has finite area, but 1 over x does not. So it has infinite area. So you just have to be careful. You really don't need to use any intuition, because intuition is sort of non-existent when you're talking about infinite bases. But that's okay, because you can just go through the calculation just using limits.